Good morning, everybody, and welcome back to another episode of An Unexpected Fight. We are joined here today by Dr. Claire Carter, and we are so excited to discuss what she's been doing. Kelly, you want to give our intro?
Yes. So we're so excited to have Claire L. Carter, Ph.D., here today. She is an assistant member of the Center for Discovery and Innovation, assistant professor of pathology at Hackensack Meridian School of Medicine, and co-director of the Mass Spectrometry and Analytical Pharmacology Shared Resource at the NCI-designated Georgetown Lombardi Comprehensive Cancer Center. Dr. Carter completed her Ph.D. in chemistry at the University of Birmingham, UK, under the supervision of Professor Josephine Bunch. She then moved to the US for a postdoctoral appointment at the University of Maryland Baltimore, where she worked on normal tissue radiation injury. At the Hackensack Meridian Center for Discovery and Innovation, Dr. Carter has built a translational pediatric neuro-oncology research program in partnership with Dr. Derek Hanson, Director of Pediatric Neuro-oncology, Joseph M. Sanzari Children's Hospital, Hackensack University Medical Center. Dr. Carter possesses a rare translational background that combines expertise in bioanalytical chemistry, clinical histopathology, and biomedical science. Her group is working using the next generation imaging techniques to develop a deep understanding of biological and transitional states of tumor cells as shaped by their spatiotemporal location within patients' tumors and preclinical models. Their focus is on targeting lipid signaling and metabolism for less toxic and more efficacious treatments in highly aggressive pediatric brain tumors. In addition to using mass spectrometry imaging for intratumoral pharmacokinetic and pharmacodynamic studies to identify more efficacious treatment regimens that can rapidly translate into clinic gain. Well, that's an extremely impressive bio within itself. And Tiffany and I, as brain tumor moms, are big fans over here. So thank
Quite
you.
long. I apologize. I should have maybe shortened that.
No, it just shows your passion and how much you've done in this world. And it's incredible. And, our listeners might have to Google a few things as to what exactly that means, but we'll hopefully break some of that down in our questions for you today.
Sounds good.
I'll start us off with the first question. Tiffany, you're on mute. Can you share a bit about your journey into pediatric neuro-oncology research? What inspired you to pursue this field?
So I've always had a keen interest in science from a very young age. It's the only thing I enjoyed at school. And when I went on to university for biomedical science and started studying disease states, they fascinated me. And when I transitioned to building my own research group, I actually started in adult brain tumors in glioblastoma. I knew I wanted to be in neuro-oncology. I knew it was, brain tumors are devastating diseases. They're difficult to treat. They're difficult to resect because the nature of the brain compared to, non-CNS organs. So I started there. And then actually my boss, David Perlin, who runs the Center for Discovery and Innovation, introduced me to Derek Hanson, Dr. Hanson, because he had a clinical trial that I think actually is still ongoing, looking at 2-hydroxyoleic acid. It's a derivative of a fatty acid found in olive oil that has shown efficacy in treating adult glioblastomas. It actually prolonged survival to the same level as chemotherapy did, as a standalone treatment. So Derek and I started working together on that. And then the more we spoke and the more we communicated, we decided we wanted to partner and build a translational pediatric neuro-oncology. And I have to say, prior to meeting him, I didn't realize there were so many pediatric brain tumors. I was quite naive to it. And then upon learning about it, and especially, ETMR and some of the rare ones that are more in the infant population, I could cry just talking about it. So I was, we teamed up and we we're funded through Tackle Kids Cancer, which is part of a philanthropic organization under the Hackensack Foundation umbrella. And they gave us startup funds to build a pediatric neuro-oncology lab. And we started that during COVID, so we didn't really start it. And then we really kind of started building everything in 2021 and started studying patient ETMR samples and trying to acquire the cell lines we need for, functional and drug therapy studies. And we're now at the stage where we are about to publish our first findings, which is exciting. But yeah, that's kind of how I got into it in a naive way. As soon as Derek and I started talking, I was all in. Really
incredible. I don't think you're alone with not realizing how prevalent pediatric brain tumors were, because I'm a registered nurse. Tiffany's a nurse practitioner. And when both of our children were diagnosed, I think we were very much taken off guard as well. It's not something you hear a lot about. That's part of why we wanted to start up, the podcast and spread awareness and interview very intelligent people like yourself and learn more. Because it's a lot more common than people realize.
Yeah, it is, and it's devastating. And the work you two do is incredible, from the foundation point and the podcast point. It is.
Well, thank you. I mean, so whenever I met you at the ETMR conference, I was intrigued by the talk that you did. And so your background is so unique. You blend this bioanalytical chemistry, histopathology, biomedical science. So how do you combine all that in your research, and how has that kind of shaped what you're researching now?
So when I was an undergrad, mass spectrometry imaging was being carried out by maybe 5 groups in the world. It was a very niche field. Everyone was proof of concept, but one of my lecturers was one of those people, and he exposed us to it. And with the biomed and the pathology background and knowing I wanted to study diseases, there was then this new technique that you could use to map biomolecules in tissue without a target, without a label. And you could also, for the first time, map drugs and drug distribution in tissue without a label. And it's, they're active metabolites. And it kind of blew my mind, and I saw the vision and I saw the potential of it in the future. So I carried out a PhD in chemistry, in mass spectrometry imaging, and developing the method and the protocol, knowing I wanted to apply it to disease states. So we take every angle we look at from a brain tumor point of view is spatial, and that's what we combine. The histology is spatial, but it just tells you, the tumor, the vasculature. You don't really know what's going on inside. And you can look at things with a technique called immunohistochemistry. Like if you're interested in Lin28, which is a diagnostic marker for ETMR, right? You need an antibody to stain to Lin28. What mass spectrometry imaging does is you can then look at all of the lipids and all of the metabolites and see which ones are in the tumor cells and what they're utilizing to help them grow. So what we're trying to do with mass spectrometry imaging is see what lipids are there in terms of biological function and what the tumor cells are eating to keep growing, right? Because they need to eat something to keep growing. And that's how I kind of break it down to people. We look at what they're feeding off, and then we're trying to interrupt that to stop growth.
For myself and our listeners, can you break down what spectrometry imaging is? How is it used?
Yes. So when brain tumors or cancers are surgically removed, that tissue is sent to a pathology department, and they then take really thin slices of it and put it on glass slides, and they'll either stain it to look at it's called histology, where you just look at the cells in there. What mass spectrometry imaging does is we acquire a mass spectrum. So we take things from a solid into the gas phase, and then the mass spectrometer measures it, right? So we can tell what's in there based on how much it weighs. I don't know if I'm breaking this down in a very good part. So we go across the tissue at predefined spatial resolution, say 50 microns. So we're taking a few cells at a time, and we map the entire tissue section. And then we have this graph readout that's called a mass spectrum that has all of these ions in that we've detected from the tissue. And then we can click on those ions and see where they accumulate. So we can look at glucose, say, and see where it is in the tumor cells. And if all of the tumor cells are using it, we can look at neurotransmitters and lipids and metabolites and just spatially overlay them with the cancer cells or the vasculature or different things in the tumor microenvironment to see what's contributing to tumor growth and aggression.
Okay. That's
so it's a kind of spatial measuring technique.
So cool.
Okay. Yeah, no, that sounds amazing. So you kind of talked about how you got into pediatric brain tumors, but what challenges make them particularly difficult to treat?
So compared to a liver or a kidney where you can take one out or cut a tumor out, in the brain, depending on where it's growing, it's not always accessible to a surgeon. And couple that with how aggressive they grow and just the metabolically rich microenvironment of the brain, it's so high, it's the most complex organ in the human body by far. It's very metabolically active, so a lot of the aggressive tumors are very, they grow fast, they spread. If things are near the brain stem, they can't be resected. And then you have the blood-brain barrier, which is a vasculature network designed to keep things out. So, keeps out microbes and toxins to protect your brain. But that means it also keeps out many drugs. So you have tumors that are difficult to surgically resect, and then you have tumors that are difficult to therapeutically treat because you can't get drugs into the tumor. And those are the two biggest caveats to treatment for brain tumors that just don't exist with a lot of, cancers that arise anywhere else in the body.
That's so interesting. And so whenever we were at our conference, the talk that you did was fascinating to me because I'd never heard of this kind of science. So you studied lipid signaling and metabolism and how that impacts tumor growth and treatment resistance. So I guess tell our listeners a little bit about your research and how you're utilizing these lipid signaling and metabolism to be able to treat cancer.
So we start with patient samples that, and this would be a great time to thank the families that have donated samples to enable us to study them, because without that, we can't drive things forward. So it's really vital. But we have patient samples that we acquired through our own hospital that Derek, Dr. Hanson's treated. And we also wrote a proposal to get samples from the Children's Brain Tumor Network, who have, this large biorepository with all the genomic information. And what we do is we take the patient samples and we study them spatially first and foremost. And then from the patient samples, we identify things that accumulate in those rapidly proliferating tumor cells. So we show that they're proliferating, we show that they're actively growing, and then we look at what they're using and what they're doing. And then we take those lipids and we make sure they're in our preclinical model, right? Because if they're in our patient samples, and our preclinical model, which is a patient cell line that we grow in 3 dimensions, but it's grown in an artificial environment in the lab. So we first need to make sure that it's utilizing the same pathways as what we see in our patient sample. And then we know we've got a good thing to study that we know is going to translate back to clinic. And we, what was the question again? I went on a tangent.
We just explain how the lipid signaling, how you're studying. That's just like a technology I'd never heard of or like used in treatments for cancer. So
lipids are they're part of every cell membrane, right? And they're used in metabolism and as an energy source. But they're also huge regulatory molecules that people don't really realize. And they signal and control cell fate. They can determine, depending on the lipid type, whether a cell proliferates, whether it differentiates, or whether it dies. And what we study a couple of different lipid classes. One that determines whether a cell grows or dies, and one that controls mitochondria, which is the powerhouse of the cell. And we also study metabolism because cells need to eat stuff to grow, right? These are tumor cells, and they're growing rapidly, and they're growing out of control, and they have a metabolism unlike most other cells around them. So what we're doing is we want to look at what they're eating, what they're using to grow, and what they're signaling to keep growing, and then cut it off. And looking at lipids and metabolism is slightly different to what most people do. But we believe by doing that, because of the highly metabolic state of these tumor cells, we can hopefully develop targeted therapy that cuts off their energy supply and their signaling supply while sparing normal tissue. So that's our goal. Derek and I were very universal in developing a program and looking at pathways that were tumor specific and trying to get away from these universally cytotoxic and brutal chemotherapeutic regimens. As you both know, a lot of kids succumb to the treatment alone because it's so bad. So that's that.
Just to kind of clarify something for our listeners, cancer cells do not feed off of one thing. Like, not every cancer cell is going to feed off the same thing. And I think that is such a common misconception on all these people. Oh, sugar feeds cancer cells. Like, kind of like every cell in your body needs glucose. That's just the way it is. So eating sugar does not make your tumor grow faster. Eating, too many carbs doesn't make your tumor grow faster. So it's like all these different mechanisms that Dr. Carter is looking at, and that's what's going to help be able to determine, like, every cancer is different. It behaves differently. It grows from different things. And so that's what she is working on, trying to find out different pathways for that, which is absolutely amazing. So just
thanks.
You gave a shout out. Sorry, go ahead.
No, you go ahead, Kelly.
You gave a shout out to the families who donated samples. So on a side note, how would somebody go about, donating, getting a sample over to you for your research if they were listening and thought, you know what, I'm very interested in this? How would they go about that? And how old can a tumor sample be? I honestly don't even know how long you guys hold on to these samples in a lab. For instance, my daughter's tumor sample is in like 3 different locations, I'm pretty sure. So how long do they hold on to them, and how could people potentially send you a sample?
That's an excellent question. So we deal with 2 kinds of samples, what's called fresh frozen. So they're surgically resected. They're frozen in, snap frozen rapidly in the vapor of liquid nitrogen, and then they're stored at -80. And then the other samples we look at are from clinical pathology labs, and they go through a process called formalin fixation followed by paraffin embedding. And what the formalin does is it preserves the tissue, and then the paraffin is infused to enable sectioning that we don't need to go into. But the FFP blocks, that's what they're called, formalin fixed paraffin embedded blocks. Most clinical pathology labs, back home, I think it's similar over here, we'll keep them for at least, I think, don't quote me on this because I don't work in a clinical path lab anymore, but they should keep them for at least 10 years post-diagnosis. So if families get access to those blocks, we could look at them 50 years from now. They're theoretically preserved for quite a lot of different things. So what we do with the lipids and metabolites, say we've found a class of lipids in ETMR that 2 classes that we're studying. And what we do is we look at the enzymes and the proteins that make those lipids, right? Because they're actually the therapeutic target, like ways to change those lipids. And we look at them in FFP blocks as well. We look at them spatially. So and you can do so much now with these blocks. You can spatially look at the genomic profile, the protein profile. There's all of these really, really advanced and sophisticated multiplexing imaging techniques now that are just phenomenal and revolutionizing kind of what we understand about tumor microenvironments and neighborhoods. So they would just have to either through their hospitals or, communication with myself or Dr. Hanson, and we can set up a transfer for them to be shipped here. The Children's Brain Tumor Network is also a good resource to put these samples in, because then, the wider community has access to them.
Awesome. Thank you for that. No, that's good to know. I had no idea that on average they were saved for 10 plus years. I think, that's good for people to know, because honestly, the science has come so far just since my child was diagnosed in 2020, and the things I'm learning now just in the last few years, I'm like, it is incredible, the leaps and bounds we've made in the neuro-oncology field specifically. So that's awesome.
One thing I found so interesting when I went to the research summit that we just went to, it was that they are able to grow these tumors in the lab and like test them, like grow whole cell lines from these tumors, which honestly, like I was sitting there getting so angry that they didn't take Nora's tissue because she had been diagnosed with COVID like 9 days before she died, but she was asymptomatic. And so like our doctor called 10 different hospitals to try to get them to do a research autopsy on her, and no one would do it. And I was like sitting there, I was like, God, that makes me so mad, because I mean, I knew what benefit it would do for science, but like I didn't know to like that extent that it could be studied outside of just her original tissue. So yeah, it's crazy. Yeah. But
So
what can you do?
we know a
We
lot of it
actually,
is still obviously in a lab, and you're, working hard every day. Can you share any maybe breakthrough or significant findings that you've had recently that might change the landscape of pediatric neuro-oncology? I mean, I know the lipid studying itself, to me, yeah, that changes the landscape. But let's say, the layperson listening to this is wondering, okay, how does this translate to a breakthrough in this field?
yeah, we're about to publish, it's under second review, actually, our first findings in ETMR. It's a mitochondrial specific lipid called cardiolipin, and it's called cardiolipin because it was first found in the heart. But it controls every aspect of mitochondrial structure and function based on the fatty acids that make up its structure. And there are hundreds of these cardiolipins in the brain, depending on what cell you find them in. And I'm actually going to backtrack a little bit, because there was a fantastic publication in 2017 that identified stalled developmental pathways as drivers of pediatric brain tumors. And basically what this paper showed and hypothesized was that actually if you hit the tumors to make them differentiate, right? So tumor cells in the brain are cells that should be neurons, right? Or functioning mature cells or astrocytes, or any number of the cells that make up the brain chemistry, but they're stuck in this proliferative state. They don't differentiate to get to where they need to be. So what this paper postulated was that actually instead of hitting the cells with chemotherapeutics and that are cytotoxic and kill it, if we can hit that pathway that stops the stalled differentiation to make it no longer a tumor cell, so it carries on where it was supposed to go to in the first place, and it's no longer a tumor cell. So there's quite a big drive in the field as well to hit that mechanism in pediatric brain tumors, because it's a less toxic route, right? If you can get the brain tumors to not be brain tumors anymore, to be the cells they're supposed to be, rather than having surgical resection and chemotherapeutics, it's a much better pathway. So with that in mind, that's kind of one avenue we set out to look at. And we've identified this class of lipids that we show is up in the cancer cells, and we've identified the enzyme that is up that regulates this lipid. And what we've just done that isn't published yet, and we're in the process of publishing, is we show that if we knock this protein down that makes these lipids, the cells die. But we think they die because they're trying to differentiate. So we're currently in the process of seeing if we can differentiate them to get them to not be cancer cells anymore once we knock this down. But it's a mechanism that we think is going to be very fruitful, because it's one that controls the cell's metabolism, and metabolism is what drives differentiation or proliferation. So that's one of our, I think, something I'm proud of and excited about.
Yeah, that's incredible.
Several years in the making. Unfortunately, everything takes so long.
I was going to say, like, the time, just so it takes so long to do all these studies, but they're so excited.
I know, like, and come on. Everybody out there who, because I hear it all the time from people who don't live in this world. How come it's taking so long to find a cure for XYZ? I hope that this brings some awareness to them. Number one, we're studying thousands of different diseases, and every tumor is different on a molecular level. But just listening to Dr. Carter really explains why there's so much that goes into it. So thank you. That is very exciting, and congratulations.
Yeah. So what makes intratumoral pharmacokinetics and pharmacodynamic studies critical for designing these better treatment plans?
This is something I'm very passionate about, because I have quite a strong background in spatial PK/PD. So pharmacokinetics is, where is the drug getting to, right? Is it getting there? Where is it getting? Pharmacodynamics is, what is the drug doing to the cells? So how is it changing? How are the cells responding to a drug? A lot of cancer treatments, as with most treatments, were developed in an era when we didn't have the advanced technologies we have today. And then additionally, pediatric cancers, all pediatric cancers, treatments extrapolated from adults, right? And pediatric brain tumors especially is extrapolated from how adults are treated, but pediatric brains are so much different to adult brains. They're still developing. Their metabolism's so different. So what we do is we use mass spectrometry imaging, because we can see exactly where the drug's getting in. And a lot of time what you'll see is you can have, say you have ETMR grows rapidly, right? Some of these tumors are 5 or 6 centimeters in diameter when they're diagnosed. What we want to look at preclinically and clinically, hopefully, is how much of the drug's getting into the tumor, right? Because we don't know. We use radio labels and show that it's getting in or it's not getting in, because you can only follow a label. With mass spectrometry imaging, we can actually look to see, is that drug getting in absolutely everywhere? Is it reaching the core? And if it's reaching it, is it working? And is it at a high enough concentration to be working? And if not, how do we change that dose? And if it's not working, what are the cells doing? Like, why isn't it working? How are the cells behaving that's making it not work? And then how do we develop better techniques to get drugs in to work better? And we're actually working with a company, we've started working with a company where we're going to start wrapping drugs. It's called solid lipid nanoparticles. So you can put drugs in these lipid, and you can get insoluble drugs. And because it looks like a biologic, we're hoping it will cross the blood-brain barrier more effectively. And we can use mass spectrometry imaging. We can change a treatment. We can look at a treatment. We can change the formulation of a drug and then say, right, this actually works much better than this, right? Let's try this in the clinic. Or, this actually isn't working and we're treating kids with it, and we have been treating kids with it for decades, and actually it's not getting in at all. Or it is getting in, but it's not getting in at the right concentration. there are a lot of background chemotherapeutics that nobody really knows if they work, right? Because it's a combination. It's a combination of four induction chemo and then maintenance chemo, and it's like which one of those are working? Are they working? Nobody really actually knows. So we're starting to study that as well, and we're actually trying to get to a stage where our models are much bigger than what's historically being done as well, to be more clinically relevant. But yeah, so PKPD, that's what we call it. It's fundamental.
Great explanation. I'm just very impressed by you. So I'm like, maybe I need to go be a researcher.
So you can come and hang out in my lab whenever you want.
Oh yes, please.
I'll add to that. So historically, right, people would preclinically they'll treat a tumor and then they'll take the whole tumor and then they'll mash it up and then they'll measure how much drug's in there. But you don't know, like if you have like a cluster of tumor cells to the right and all of the drugs on the left, and it's not even getting into the tumor, but the area you've measured, you can't tell. So with the spatial analysis with the mass spec, we can actually say it is in these tumor cells, it is in the microenvironment, or it's just actually hovering around the outside and it's not getting into the tumor cells. So that's the benefit of the spatial analysis.
Awesome. Now, what are the biggest hurdles in translating these incredible lab discoveries that you have going on into real world treatments for children with these aggressive tumors?
They're lab models. They're not human. And a lot of the time, things don't always translate because of that. I think the models we have now with the 3D tumor models and the patient primary cell lines have actually improved significantly, and there has been quite a few breakthroughs recently, I think, because of that, like ONC201, ONC206 for DIPG is in a couple of clinical trials. It's shown efficacy, and that preclinically was also shown to be a mitochondrial-driven differentiating drug. So I think half the battle is getting the models more clinically relevant, which is difficult because it's not a patient sample and it's never going to be. But I think as the years go on, we're getting closer and closer to refining that in a much better manner. And because we understand the tumor microenvironment a lot deeper now, a lot more, things are improving. But they're the biggest caveats. I think.
And the more and more tumor samples you get, the better that's going to be,
Yes.
Because you're going to have, all the different genetic components, all the different, more samples, the more you're going to learn from it.
Yep. And we're also, so we're trying to make drug-resistant cell lines as well. Like vincristine is one of the backbone chemotherapeutics to ETMR, but we see what looks like a slight bounce back at a higher dose, which is a bit unusual. So we're also trying to see if we can low dose or dose these cells in a way that they actually start becoming resistant, because there are no cures for some of these tumors. So they are resistant to the drugs, or the drugs aren't getting in. So that's another thing. It's getting the patient samples that recapitulate that complexity and that drug resistance and how they change. Because once you treat a cell, it changes. Right, and it starts to not respond to that drug. It upregulates stuff. It starts being different. So we have to start really building these models up. And with ETMR now, there was traditionally just one cell line, which we've all been studying. And as you know, Tiffany, with Marcel Call has now 5, and the group in New York at Cornell have a couple. We have 2 additional ones we're trying to establish, and that's really where the game-changing things start to come in, because then we have representation of this complexity rather than just...
Do you feel like rebiopsy, and I know this is technically would be very difficult to get multiple biopsies as a patient either relapses or progresses, like versus their initial diagnosis, do you think that would be helpful in helping figure out like resistance pathways and what the tumor's doing to change as we're going along?
Yeah, Absolutely. Because these are all, they're classified as ETMR or ATRT or ependymoma, and then they're subgroups based on their genomic profiles, right? But the tumor microenvironment of all of them is so different. And then you add in treatment, it becomes so different again, and they have transitional states. So yeah, the more that we can collect is always the better.
I mean, what I would also find interesting, so Kelly's daughter had GBM, infantile GBM, and survived a stage 4 infantile. And so, like, I think that'd be so cool to study her daughter's tumor and see why, like, what she had in her tumor, the microenvironment that made that so susceptible to what treatment that she got. I think that would be fascinating research as well.
Yeah. And I bet it was post-treatment maturation and differentiation. There are, if you look in the literature, there's a handful of these studies, and they come out more and more, where we published a case report in ETMR as well that showed after treatment the tumor cells turned into, they differentiated along their pathways. But surviving GBM is no small feat. That's amazing, and it's such an incredible thing to hear.
Yes.
It gives hope, doesn't it?
Absolutely. Absolutely. I share her story as much as I possibly can.
Good.
And I appreciate, you going into this field, because that's what, pediatric oncology is difficult to begin with, but studying neuro-oncology specifically, I mean, you picked the hardest one to try to break down. And for that, we admire you so much. So it's just incredible. How do you collaborate with clinicians like Dr. Hanson, who you work with, to ensure that this research directly benefits patients? So how do you guys kind of collaborate?
We have a 100% partnership. We have group meetings together every week, and we present the preclinical data. We go over his clinical stuff, and Derek's involved in a lot with his ETMR1 registry, and then the clinical trial they're trying to get up and running, and he does a lot through PNOC as well. We're also part of the Children's Brain Tumor Network, so the scientific committee and the PIs have monthly meetings with that, and people present their projects that they've done through that. So it's, I have to say, out of all the field, because I'm new to pediatric neuro-oncology, right? I'm 4 years in. I'm not a strong cancer researcher. I'm not a strong neuro-oncologist. I come at things from a completely different angle to everyone else. And having that clinical collaboration is fundamental to driving things forward. And the pediatric neuro-oncology field, I feel like, is miles ahead of the rest of the pediatric cancer and even adult cancers in terms of international collaboration and camaraderie and working together to really push things forward. And what people have done in the field over the past 10 years is just so commendable, to where they've got it to. It really is. So I'm really hopeful, with the technology we have, and the international collaborations and the things like PNOC and the Children's Brain Tumor Network, and the connections that everyone has through that we can really actually start moving the needle with some of these.
And I have to say, don't just say you're just 4 years in or you're a newbie, because you're coming in with like a fresh new idea that may change the way brain tumors are treated. Like, seriously. And I think that is something to really be proud of yourself for. So you're not just a newbie or, just a regular researcher. You've got some ideas that really could be groundbreaking discoveries for these treatments. But what, in your opinion, is the most promising thing that you think is in pediatric cancer research today?
I'm biased, but metabolism.
Yeah.
I'm completely biased, but metabolism. It's a hot topic in all cancers at the moment, to be honest. Metformin's an anti-diabetic drug that's in over 400 clinical trials for all cancers, as part of therapy. There was a pediatric clinical trial completed a couple of years ago, and it showed efficacy in a patient with glioblastoma, but the authors, were like, we need more preclinical data on this. So metabolism, I think, is the most exciting thing and the most interesting thing. And it's never going to be one treatment, right? We're not going to do that. We're going to have to hit these down at different times from different angles. But I think metabolism really, especially for a differentiating drug treatment as well, I think is the key.
Absolutely. And we all know that we need more funding for these studies to take place. So pediatric cancer is notoriously underfunded. What do you think needs to change to accelerate this
funding? I think an awareness, because I know the NIH budget, people throw around 4%. I think it's gone up to about 11 now. I think the 4% is a bit historic, but I think that the more information we get out there, and the more information you get out there through what you do, through the foundations, through this podcast, to raise awareness that this is actually, this is a real thing, and it happens, and it's devastating, and it needs funding, and it needs support. I think is what we need. My lab is 100% funded through foundation money. Like I write NIH grants regularly, but from an academic standpoint, I'm told regularly by more grown-up professors, you have to write 10 grants and have 10 grants to hopefully get one funded, and that's the nature of it. And Derek and I we're up to about 5 different grants that we're submitting around now. It will be 6 or 7 by the end of the year with different things, but it's notoriously hard to get funded. And I'm so grateful for Hackensack Meridian House Foundation and their Tackle Kids Cancer drive, that they raise money through philanthropic donations, but through a lot of foundations as well that donate to our lab for us, to be able to do this research. So I think it's just, awareness, fundraising, to get the money into where it needs to be for the research to happen.
We have a soft promise to give y'all some money in the summer, so we get it raised. We're trying. We're doing our best.
Well, if you need help, let me know.
I know. I'm like, girl, listen, we need all the help, all the money, guys. So if y'all want to donate, this is some really cool, impactful research. I'm telling you right now, this is going to be good. It's going to be really good. So how can advocacy groups support and advance pediatric cancer research? Obviously, kind of like what we were talking about, advocacy for just making awareness, funding. So, maybe just talk a little bit about Tackle Kids Cancer through Hackensack so people kind of know what that is. Like Kelly works for a different foundation. I have my own foundation. So we're obviously not in this all separately. We're not trying to compete against each other. Like, donate to whatever foundation you feel like you are being led to donate to. So, and here's another great option for you guys.
Yeah, a lot. So the lab's funded through TKC, Tackle Kids Cancer. Eli Manning, the quarterback, the retired quarterback, is actually part of our fundraising campaign. He partnered with the hospital, and it predates, me and the Center of Discovery and Innovation. But it comes from people that have, a lot of the donations come from people that have been impacted by pediatric cancer, obviously. And, a lot of it is locally in the tri-state area, but it comes from foundations. Josephine's Garden, Heidi Rispoli lost her daughter to ATRT. She was treated at Hackensack, over 10 years ago now, and she's set up a foundation in a similar way to how you two did, and has been fundraising every year and donates to Tackle Kids Cancer for the lab specifically. There's Team Campbell in South Jersey lost their daughter to appendymoma, built a foundation out of it, and that's kind of the heartbreaking thing. It's all of the money for cancer research is born out of people like you that have been impacted by it, realize there's no research, built foundations, fundraised to enable our research to even happen. Like the breakthroughs that we have unfortunately and heartbreakingly have come because you've all suffered. And that's the reality of it. So people need to get out and, you know, the NIH needs to do better as far as I'm concerned. It needs more of a pediatric focus. Specifically, I think it should have its own IC center. There should be a large sum of money that is designated just for pediatric cancer. But, you know, the more people talk about it, the more people fight for the cause, the better.
I say it all the time. Please help us and get involved before it does affect you personally. You know, it doesn't have to affect you personally for it to matter. It could be your child, your grandchild, your niece, your nephew, a cousin. So thank you for
It's
that.
heartbreaking. I get emotional talking about it. I'm a very empathetic person, and it is, you know, it's heartbreaking. So
Absolutely.
Would have never have been a cancer parent in my head. That was never going to happen
Right.
to me.
no,
I don't know anybody that's had cancer. I mean, my family's had cancer. That will never happen to me. I feel really terrible for the people that happens to. And then it was me.
So, Dr. Carter, where do you see pediatric neuro-oncology research in the next 5 to 10 years? I know, we've talked a lot about the metabolism and the lipid studies and the different things you're doing in your lab. But maybe, what else is on the horizon, or what part of that gives you the most hope?
I think the technological advancements that we have now, and that just keep getting better and better, and you know, AI machine learning algorithms that can really mine these big datas, and the wealth of information we can obtain now will really help us break down what's going on with these tumors to help us identify better treatments. I truly believe that. And then from a pediatric, you know, neuro-oncology standpoint, the work that CBTN and PNOC and everyone else is doing on a collaborative manner, and the way that clinical trials, I think, are being designed now for the treatment of pediatric cancers, where, you know, if something is shown to work preclinically, it can be umbrellaed in, I believe, is the way they're being built. It's more of a Dr. Hanson question, though. You know, so I just think everything's being done a lot smarter with a lot more information now, and I really hope. I'm really positive for the next 5 years that we are actually going to, you know, start moving the needle with some of these treatments.
Absolutely.
What advice would you give to young scientists or medical professionals that are wanting to make a difference for cancer research or pediatric cancer research?
Do it because you care, and then that way you'll make a difference. It's probably, you know, if you're passionate about enacting change in something, it's not a job, it's a privilege, and you know, and that's when change happens, I think.
Absolutely. Now, what keeps you personally motivated in this extremely difficult but important field?
People like you, honestly, and the stories I hear, it's heartbreaking. No kid should go through that ever, and the surgery and the treatments are absolutely brutal, and it's years and years and years of stuff on repeat, hoping that you come out the other side okay. So that's just what keeps me going, hoping that in some small way, if I can make any contribution to making any of that a little bit better, that's kind of what keeps me going.
Thank you for that.
Well, you're incredible. How can our listeners get involved with supporting your work, your team, follow up with what you guys are doing?
Samples and donations. They're the big two. They're the big two. And if you two ever need anything, let me know.
Hey, I'm gonna be in New Jersey this summer, so
Well, let me know.
I'm gonna be like, let me come in that lab, please.
You can come in the lab and then we can go for a drink after.
Yes, let's do it. Let's do it. No, I thank you so much for letting us talk to you and explaining about your incredible research. I think that you are going to be moving a needle in the next 5 to 10 years, and I'm really, really excited to see the difference that that you make through all this. So if you want to get involved with Gold Ribbon Kids or the National Pediatric Cancer Foundation or Tackle Kids Cancer, we're going to have all the information in the show notes. We thank you so much again for listening, and we'll see you next time on An Unexpected Fight.
Thank you.